Everyone. So today it's my pleasure to welcome Anirbit Mukherjee. We'll be talking about provable training of two-layer neural net.
I'm starting off then. Hello.
Yeah, you can start. Yeah, you can start. Yes.
Thanks for the invite. I've always wanted to have a chance at speaking at this One World seminar. So thanks for this. Finally, the opportunity has come. Thanks a lot for the invite. So this talk, I will present a sort of a survey of 3 or 4 of our major results over the last few years about provable deep learning. I'm not sure how many people in the audience are familiar with neural networks. So in case someone isn't, here is a simple neural net to keep in mind. What you see on the screen is a R2 to R map. 2 numbers go in at the green edges, the green vertices, x1 and x2. The topmost blue vertex is a ReLU gate, which computes the max of 0, the sum of the 2 inputs, x1 plus x2. That's what the edge weights mean. The second blue gate computes max of 0, minus x1 minus x2. That's what the -1 weights of the incoming arrows to the blue gate mean. Then you're combining the outputs of the 4 gates with weights half, minus half, half, and half. And you can convince yourself that this particular weighted linear combination that is coming out of the red gate is actually the max of the 2 input numbers, x1 and x2. So this is a very simple example of how a neural net can compute the maximum of 2 numbers. And historically, in terms of the last 5-6 years of research in deep learning function spaces, this has turned out to be a very important insight that neural nets can compute max of 2 numbers. This can be used to get very interesting research results can be gotten by using this in a very careful way. So max computation is a very nice example to keep in mind of what neural functions look like. Okay, so this is a formal definition of a neural network that we think of ReLU activations as being Rn to Rn maps, so each coordinate passes through a max of 0, the input. And a depth k plus 1 neural network will be a k plus 1 times alternation of affine transforms with ReLU gates. The input comes at A1, it comes out of the affine transform A1, passes through a layer of ReLU gates, passes through an affine transform A2, and it does it k plus 1 times. And that's what you get a k plus 1 depth neural network. The width is the largest inner dimension. So there are k plus 1 affine transforms here. The largest inner dimension is called the width of the neural network. And we don't assign weights to the edges of the graph. So for example, what you see on the screen is an R4 to R3 map it is a potential R4 to R3 map with the edges not having been their weights assigned. In such a situation, this architecture is to be read as a specification of a function space. So you have a whole class of functions coming out of it by every possible assignment of weights to the edges. So it's good to keep in mind how to go back and forth between architectures which specify function spaces and a particular neural function. And why are neural functions exciting? For experiments like this, I would say. To start off, like these are human faces. These look like human faces, but these are not photographs of any human being. These are outputs of neural networks. So there's some very complicated mechanism. We could figure out how to assign weights to the edges of a neural network so that the output looks like a human face. And that's fascinating to someone like me. Like, how on earth could you find out the weights so that output looks like a human face? So then this kind of thing is still far from being explained, and why the subject is still alive. And one day we want to explain this, and that's the eventual goal. Okay. And the reason, one of the deep mysteries with deep learning is the fact that ultimately it's an optimization problem. We have to frame it as an optimization problem. Search for a good neural net that will produce the best human faces is ultimately an optimization problem. An optimization problem, the objective has to be nice enough in some way for standard ways of thinking about it to work. But it turns out that the neural landscape is not nice in any simple sense. As you can see on this diagram, the left-hand picture is the neural landscape, the actual objective function. And if you do a very small change to it, actually the picture moves from the left to the right. And the right one looks much more nicer. And it's very hard to know analytically at the beginning as to whether you're in the right picture or in the left picture. And this extreme sensitivity to the architecture is what makes neural deep learning such a complicated field. And despite, so far one part is that we don't know where the sensitivity comes from. I cannot tell you whether it is the right picture, the left picture by any simple calculation. If you give me an architecture loss function, I don't know which picture you are in. That's just too hard to figure out. But the thing is that we don't need to figure out it often enough. In the real world, it turns out that the algorithms are trivial. You can write 5-line pseudocodes that will work perfectly fine on a million-dimensional neural network, and I can give that as homework problems to my students. So my students in their homework problems are training multi-million-dimensional neural networks regularly. So undergrads are training million-dimensional neural nets without any thought. But why is it working? That's the mystery. If neural net training was hard, the subject would not be there. The whole point is that it's easy to train neural nets. It's super easy to train neural nets despite this incredible complexity of the function. And that is the mystery that we want to explain, and that's we're still trying to explain. How do simple algorithms work when the objective function is so much more complicated? Okay, so let's see. I will start with some results about non-gradient training of neural networks. That's a line of research that we have been doing for quite some time. So way back in 2016, we had shown this particular theorem, which had caught quite a bit of attention in 2016, where we showed that for a depth 2 neural network of ReLU gates, no matter what the data is, no matter what the width is, you can always find the global minima exactly in a time which is not exponential in the training data. It is exponential in the width for reasons that I'm not going into. It's extremely complicated area of research as to whether the width exponentiality can be ameliorated or not. At this point, there is some very interesting result by Adam Clavance's group saying that essentially the width exponentiality is removable up to some complexity conjectures. The runtime is exponential in the input dimension. That is easier to understand because that is a much more classical NP hardness result. But the most interesting thing happening in this result is that I can find the global minima in a time which is polynomial in the number of training data. So for a fixed architecture, you can find the global minima of depth 2 neural networks in time that is polynomial in the training data size. And that was an interesting result at that point. It's still very interesting because there was no complexity theoretic proof before this to show that there is a hardness, that there is at all a complexity theoretic hardness in the training data size. It shows that there is no such hardness barrier. And this kind of a result is completely unknown for multi-depth ReLU gates. As far as I know of, there is only one such result at this point at depth 3 nets where you have a single gate in the third layer. So except for a very restricted depth 3 net, we are not aware of this kind of polynomial training data exact training for any other depth neural network at this point. And neither do we know of any complexity barrier to it. So it's a hugely complicated mathematical open question. Either prove a complexity barrier at high depths or prove that there is an algorithm. We don't know which way it goes. So this is one kind of algorithm, which I would call exact algorithms. Okay, it is possible to find exact global minima of certain neural networks under pretty general conditions. Okay, but there are restrictions on the depth, as this is a depth 2 result, and proof of trainability is open for almost all realistic parameterities, which is at finite sizes without fixing to specific data distribution. If you want to do provable training, this is not clear for most things out there. And in 2020, we solved a number of core mathematical challenges to be able to answer this trainability question at what I would call is the trifecta of 3 properties. Like a good training proof should have 3 properties. One, it should have 1 or more ReLU gates. I mean, at least 1 or more ReLU gates is one of the things I focused on at that point. And the data should be non-realizable. And third, the algorithm should somewhat resemble SDE. Okay, it should not be too different from SDE either. Well, after all, most real-life algorithms can be thought of as a complicated version of SDE. Most of them can be thought of. And particularly the good ones, definitely. So you want a proof which has these 3 properties together. And that has been an adventure we have been on for quite some time. And I will present 2 key results that we have about provable training in this particular zone, which I would call as the most interesting zone of provable training. So the first result we have was this particular algorithm that we wrote down. This is training a single ReLU gate in a supervised learning setup when the true labels are an additive probabilistic distortion adversarially done to the true outputs of a ReLU gate whose weight is W star. So this is a data poisoning setup. So by being in the data poisoning setup, I am not being in the realizable setting. My data is not exactly realizable in the function space. I'm allowing an adversary to do online attack on my labels. It's a bounded probabilistic adversary. And I'm going to take gradient-like steps, not a true gradient steps. So the GT that you see on the screen is not the gradient of the loss function. It is a slight modification to the true gradient. And this modification is what I've marked out in red, that it thresholds, it does the update only if the label is greater than the largest perturbation, largest attack the adversary can do. This turns out to a very neat trick. If you actually did SGD, the cutoff here is the predictions being greater than 0. That's what you'll get when you do, you take the subgradient, or what you call a proxy gradient of the ReLU activation. In the truly what you do in the experiments is you take some kind of proxy gradient of the ReLU activation. Proxy gradient of the ReLU activation will put a cutoff on the output of the gate. And that's what SGD, quote unquote SGD, but this is not a gradient descent, not a true gradient, what we'll do. But we change the indicator. We change the cutoff to be on the labels rather than the weights. And this very small tweak turns out to be a mathematical magic. Suddenly the algorithm is provably convergent. It converges to the global minima. And not only is it provably convergent to the global minima, it is convergent in a sense which is robust. What I mean by that is that if you see the two plots here, what I'm showing is the parameter error of recovery with iterations of the algorithm. And the left one is our provable algorithm. And the right one is the true stochastic gradient descent behavior at various different attack thresholds. The theta star is the amount of attack the data poisoning adversary is doing. And you can see that the two algorithms dynamics is largely similar. So somehow I'm able to replicate SGD's true dynamics, some properties of SGD's true dynamics, while keeping the provable algorithm. Well, if you try writing this proof in the SGD setup, we have no idea. It's currently, as far as I know, we do not know how to do this kind of SGD proofs with this kind of setup. Definitely not with an attack. What is the controlled behavior of SGD under data poisoning attack on a ReLU gate is currently not known to the best of my knowledge. But by this small change, I'm able to get a convergent stochastic process while my dynamics is very close to being actual SGD. And this happens also from the attack side. So in this plot, what you see is the right-hand side is SGD, left-hand side is our modification, and I'm changing the probability of attack from 0 to 0.9. So like almost no attack. The blue line is no attack. So it's a exponentially fast convergence to global minima. The blue line is shooting to the global minima exponentially fast. And then I'm slowly increasing the attack probability, and it's deteriorating in a gradual way. And SGD does deteriorate in a gradual way. There's no discontinuous jump anywhere. And that's exactly what happens in our algorithm also. So whether you're from the attack point of view or from the probability of attack point of view or the magnitude of attack point of view, we can replicate some of the key features of SGD in zones where SGD is not provable, but our algorithm is a provable convergence, has provable convergence. And this idea can be taken quite a bit far, that you can modify the SGD in controlled ways so that your stochastic process is provably convergent. And that has led us to a couple of more results. And to emphasize, this is probably the only example out there of linear time convergence on a ReLU gate, while neither fixing the functional form of the marginal distribution nor making a symmetry assumption about it. So I'm dropping two assumptions at the same time. I'm not assuming in Gaussianity or anything like that. It could be anything out there, except for some moment finiteness. And I'm getting linear time convergence. So to the best of my knowledge, there is no other proof at this point which can show linear time convergence on a ReLU gate in distribution-free setting, which is what we achieve here. And also we can give controlled behavior under an attack. And this story can actually be moved to the multigate setting. So more recently, we have been able to show that what are called Tron algorithms. We have been able to analyze this idea called Tron algorithm. We have generalized the idea of what a Tron algorithm is. So there's a history to what are called Tron algorithms starting from 1980s almost. So I think one of the most famous ones was in 2010 probably, was called GLM Tron algorithm. The GLM Tron algorithm has been modified many times. There's a GLM-tron, there's convert-tron, there is sparsity-tron, then there is, I'm forgetting a few more names. There are quite a few tron algorithms out there. So what we did was we looked at all these different tron algorithms and we were able to come up with a generalized notion for tron algorithm here. And we showed that this generalized tron algorithm has a key insight in it, which we were able to isolate. And I was able to show that it still has a, now we can get multigate convergence. Again, linear time convergence in the distribution free setting, but this time I require a bit of a symmetry assumption on the distribution to get to multigates. And this is still, it's a multigate convergence with linear time convergence, which is again replicating the SDD behavior. But here something more happens that I'm not going into the details in this talk. So this in fact is actually the only theoretical analysis of a multigate neural regression in a data poisoning attack. So there has never been this analysis of data poisoning attack on a neural network during a regression setting has, to the best of my knowledge, not been done before. Hundreds of papers have been written in the classification setting. There's a lot of research has happened on the half space or the ReLU gate, just a single gate under classification attack, which is something called the Massart noise. So provable learning under a Massart noise is a well-established field, pretty much, but it has never been carefully thought about as to what is the analog of the Massart noise problem in the regression setting. So to the best of my knowledge, this paper shows for the first time a formal mathematical framework of asking the question of what is an optimal regressor under a label poisoning attack with multigates. And here is an answer. But what is more interesting is that this result, in fact, we show that our resilience to the attack is in fact stronger than SDD. So this is something more happening in the multigate setting. So I'm able to buy a stronger resilience to SDD. And in fact, the experiments that we have done in this paper show that the resilience to SDD survives even under heavy tail data. So when the heavy tail data, SDD goes quite bonkers. If there is label attack under heavy tail data, SDD is best of luck, not happening much, but this algorithm is still stable. So, and that is somehow not yet mathematically provable. We do not know how to prove convergence of this training algorithm with heavy tail data. And that's a very interesting mathematical question. I think that is currently open. Are there any questions so far? Any questions anyone can ask before I go into the more very different parts of the talk I will get into from now? Are there any questions? Then I can take some questions at this point.
I could ask a quick question.
Yes.
Yeah. When you mention SGD, is that including noise? Is that noise essential or you can run SGD without noise, right?
What do you mean by noise in SGD? SGD is a stochastic algorithm. So do you?
Yes, but if you assume that you can you have an empirical risk minimization problem, you have finite data,
yes,
then you can run the batch size which equals to the size of training data. And in that region, you don't have noise in the gradient.
No, this is so batch size equal to training data is not a stochastic gradient descent at all. That's a pure gradient descent.
Yes, then in the pure gradient descent algorithm, does that have similar behavior compared to SGD or not, in terms of global convergence?
If I think it is good question. I do not know if anybody has analyzed gradient descent on a single ReLU gate. I would believe that since SGD has been proven for a single ReLU gate, I would think the same proof would just simplified version would work on pure gradient descent. Because typically gradient descent proofs are easier to write when you have an SGD proof. Since we already know SGD converges on a ReLU gate under realizable data, I would expect the same proof, a simplified version should show you the convergence of GD. That would be my guess, because typically GD proofs are easier than SGD proofs. And if I already know SGD converges, I would expect GD proof is just the same thing.
Yeah, that's my question. Okay.
Yeah.
Okay.
So, but in our case, we're always having a mini batch. So in all our, so just let me just take up this lighting has to be fixed. The lighting switches off here. So in our results here, always there is mini batching. So we always keep track of the mini batch size. So this is fully stochastic. Okay. So now let me going to the second part of the talk, but I want to do some literature review before I get there to motivate the question in the second part of my talk. So gradient-based training is extremely successful in the real world, and it's a very simple algorithm, and it's widely successful across multiple training regimes, and we don't know why. And that has largely remained unexplained. So in the rest of the talk, I will establish, probably for the first time, that stochastic gradient descent converges to the global minima of certain neural loss functions with no assumptions on width of data. And that is, I think, important. That so far, nobody had shown that SGD can converge on nets when you remove the data assumption and the width assumption simultaneously. And I will try to explain that this is possible in the rest of the talk. So to put this in context, let me give a history of effort so far in this field. So one of the most potent directions of effort has been the neural tangent kernel approach, where people have been assuming that the width, suppose your width is scaling inversely with your target accuracy. So like if your epsilon is your target accuracy, your width is some 1 over epsilon function, some function of 1 over epsilon. The smallest known requirement, I think, is a result by G and Talgarsky, which used polylog 1 over epsilon width to get a linear time convergence. And this regime is unrealistically large, obviously, because epsilon can be very small. Then you're looking at widths which are simply not in the real world. In the real world, widths are very small. No one generally trains large width neural nets. That's not a thing. I am running currently experiments with width 10, and they can solve a lot of complicated things at width 10 already. And this kind of proofs will kick in at width 1000 minimum. So there is a complete disconnect in terms of just parameter regimes between NTK proofs and the real world deep learning. But there's something more subtle about NTK, which is mismatched with the real world. And this can be revealed by doing careful studies of how individual data used in a SGD update affects the predictions at other data. So how is information communicated between two data points in your data space? This is a very subtle thing that one can track in experiments through different ways, which we have been trying to call as elasticity functions. Then using that point of view, one can show that there is a fundamental difference in the dynamics of NTK limit point and real world nets. They're just not the same things. The limit point is a linear function in a certain way. It is a linear function, the limit point. It's a convex optimization, the NTK limit, but it's a fully non-convex problem in the real world. So this disappearance of the non-convexity can be seen in many ways. One of the interesting ways is what I would call is the local elasticity way of thinking about it. And you can see this paper of ours that I referred to, where I've explained how the NTK versus real world difference can be revealed by the elasticity point of view. So that is one kind of attempt that has been done, this NTK approach. The other approach is the mean field approach. A lot of research has happened on the mean field approach. Here, the key idea is to formulate the study of neural weight dynamics during training as a dynamics in the probability distribution of a space of weights. So what starts off as a non-convex optimization problem in finite dimensions is replaced by an infinite dimensional convex optimization problem, because you're turning the problem of optimization in the weight space into a optimization in the space of measures of weights, over weights. This is a mathematically very attractive approach, and a lot has been written. But again, this is meaningful only for infinitely wide nets. It's not even an asymptotically wide net. It's not even 1 over epsilon now. Now you really need the width to be infinity. So one can really look into how the mean field proofs work. The only way those proofs work is if you're sitting at infinity, essentially. And not even infinity, you need the continuum of weights. So it really breaks the structure of what is a neural network. So mean field training is quite different from what is actual deep learning. And let me give a summary of some of the best results in the field, what has been done so far. So 2015 was when the first convergence and multigates appeared. It was for realizable data with restrictive assumptions. Of score function had to be known. This was the Jamzamini et al. 2015. This result has been recently improved in a paper by Avasthi et al. In 2021. 2016 is when we gave the first deterministic any width, any data provable exact convergence. 2017, Zhong et al. Gave the first gradient descent convergence and depth 2 nets, but with realizable data. This was improved a lot in Zhong et al. In 2019. This actually answers the question that somebody asked last time. So this is the paper I was trying to recollect, when people have shown gradient descent convergence and depth 2 nets with realizable data. 2018 is when the lazy differential programming approach appeared by Chizaz et al. First NTK results also happened the same year. 2019 is when the first multi-depth NTK happened, the Alan Zhu et al. 2021 is when the resonant convergence was shown through mean field. So high depth mean field was not clear till 2021. This was a Kong-Fang et al. Had done this. Kong-Fang was sitting next door to me basically when he did this proof. When he published this proof actually. So this was done in high depth ResNet. They were able to get mean field convergence. So this is a very short survey of 500 papers in the field. But the basic point is that in summary, it has remained an unresolved challenge to show convergence of SGD on a neural architecture with constant number of gates and neither constraining the labels nor the marginal distribution. If you remove the labels, no label constraint, no marginal distribution constraint, no width constraint. If I remove all the constraint, what happens has never been clear. And that's what exactly is the problem that I will try to solve. So how do we go about solving this? So our story starts in 2020. There was this very interesting paper by Bin Shi, Wei Ji Su, and Michael Jordan, where they analyzed the effect of learning rate on SGD by studying the continuous time limit of SGD, which is a particular SDE. And they formally considered the following SGD. As you can see, it's a very standard SGD with a step length S, mini batch size capital B. Very standard SGD. So there is nothing funny going on with SGD. And that's what was the key thing in their paper. The SGD was completely standard. And now they were able to analyze what happens to the SGD. And they said that they were able to prove that the constant step size S SGD is actually close in this finite time horizon sense that given any finite time horizon, SGD updates are provably close to a certain SDEs dynamics, which is what you see on the screen. And this is like a constant covariance. The Brownian motion coefficient is constant. It is square root of the step length of the SGD. That's very critical in how the proof works. The Brownian motion has to be multiplied by square root of the step length of the SGD. And they were able to show that, I mean, they basically invoked a lot of previous old results known about SDE convergences to argue that under a finite time horizon, this actually is close to the SGD. And they were able to go back and forth. That if you could get the SDE convergence, you can go from there to SGD convergence. That this is possible was the key insight of their paper. And the way this proofs worked was to show that the density of the weights evolves according to the Fokker-Planck's Woluszowski PD, which is a very, very famous PD. It comes from the forward equations of SDE. So partial time derivative of the density is the gradient of the density times the gradient of the loss plus S by 2 into Laplacian of the gradient of the density. So the density evolves along the Fokker-Planck's Woluszowski PD. This was the key thing that they had used. And they had shown that when L tilde, the loss function, is a Villani function, the Fokker-Planck PD converges to the Gibbs measure, which then could show is this particular Gibbs measure. And Gibbs measure of the loss function. So if the Fokker-Planck is converging to the Gibbs measure, you are in high probability you're attaining the global minimum. That's the meaning of convergence here. The idea of Villani functions was, I think, first explained in some way in this particular structure by Cedric Villani's 2009 monograph called Hypocoercivity, a very famous book by Cedric Villani from 2009. And that's where I think first time this formally it was defined, this condition was isolated. And we know that this Cedric Villani's condition of what he was calling as hypocoercive functions, the Villani functions, they actually now have a particular role to SGD, has a particular connection to SGD. SGD and Villani functions are neatly tied into each other. And this was established by these guys. Okay, so what is a Villani function? To formally define it, RD to a real valued function on RD will be said to be Villani if it satisfies these four conditions. First is it's infinity. Second is it blows up at infinity in all directions. Third is its Gibbs measure is integrable, essentially. E to the power of minus 2ff by s is integrable, but it's integrable for every value of small s. And the fourth condition, which is the critical condition, that negative of the Laplacian of the f plus 1 over s norm square of the gradient diverges to infinity. So as you go towards infinity, your norm square of the gradient has to blow up faster than the Laplacian of the function. So and that's so that the difference blows up to infinity. And this is a very tricky condition. And this is the real meat of the Villani condition is the fourth condition. This particular balance between how the Laplacian grows at infinity and how the square of the norm of the gradient grows at infinity. And any function that satisfies the first three conditions is said to be a confining function. Okay. If people have questions, I can take them now before I go into more details. So key to the argument of getting non-asymptotic convergence is the fact that the Gibbs measure, which is the stationary distribution of their SDE, satisfies a Poincare type inequality. And they were able to show this Poincare type inequality that the variance of any compactly supported infinity differential function is upper bounded by step length times the Poincare constant in the expectation of the norm square of the gradient. I'm calling it a Poincare type and not Poincare because this is not compactly supported. That this is not a compactly supported version of the standard Poincare inequalities. And this was key to it. So the Villani function induces Gibbs measures which satisfies the Poincare inequality. Okay. And in their paper, in page 9 of their paper, they had a very interesting comment that some loss functions used for training neural networks might not satisfy this condition. So they had this very intriguing comment on page 9, and I took that comment seriously and I started investigating this thing. Is it really true? Let's see. So I come up with this setup, which is very standard setup. This is squared loss regression over any training data, any width of a depth 2 neural network with a Frobenius norm penalization on the first layer weights. It's very standard penalized regression over neural networks. And I'm going to make some assumptions about the activation function is that it is bounded, it is infinitely differentiable, it's Lipschitz smooth. Just keep sigmoid or tanh in your mind. That's exactly the condition that they all satisfy being, they satisfy the conditions that we need them to be true. Okay. Now, we can relax the bounded assumption at the cost of foregoing discrete time convergence. I can't get discrete time convergence if you have unbounded smooth activations. That's a bit of a technical issue at this point. Okay. And this is the main theorem. Given all these assumptions, I can prove this key theorem. We can take all the time we want to understand what the theorem is saying. It says that if your loss function is this regularized squared loss over depth 2 neural networks in any data, then there exists a computable threshold of regularization, which I'm calling lambda critical. There exists a lambda critical such that if my regularization is above lambda critical, my loss becomes a Villani function. So neural losses can become Villani functions if you regulate them above a certain threshold. There's a critical threshold, and the threshold is computable. Once you are sitting in the threshold, I can come up with a definition of the step length. It is given in terms of some arbitrary constant, some constants which are hard to know, but it's in principle knowable. It goes inversely with the gradient Lipschitz constant. It goes in proportional to the target accuracy, basically order epsilon. Think about order epsilon step length. You can think of it as such that if you initialize it from a certain ball around the Gibbs measure. So the Gibbs measure at the step length. So in the space of probability measures, you have the Gibbs measure at your step length, and there's a ball around that, which is what this inequality is specifying. And this ball is exponentially larger compared, it goes exponentially large compared to in the time scale t, time horizon parameter t. So basically we can specify a ball around the Gibbs measure in the space of probability distributions, such that if you initialize anywhere in the ball, initialize from a distribution anywhere in the ball, then we can get expected loss at t by s star to be epsilon close to the global minima, global infimum of the loss. And this is, note that this is not telling you a particular initialization. It's not like NTK where there's a very particular initializations are required as far as I've seen of all the proofs for the proof to work. This is not tied to any one initialization. It gives you a family of initial distributions. As long as you sample it from anything in this family of distributions, and if you have a regularization above a certain critical threshold, SGD will converge to the global minima of the neural network. And note some things like if you normalize the weights and the outer layers to 1, you can show that the critical value of the regularizer is 0.125 for sigmoid gates. This is for sigmoid. So to keep a number in mind, for sigmoid gates, that critical number turns out to be 0.125, 1 by 8. It's computable threshold. As long as the regularization is above 1 over 8, you're fine. SGD proof will work. So critical part of the proof is to show that the third condition of being Villani, the fourth condition of being Villani is true, that this limit is divergent. And this is the critical thing that sets the regularizer. It's very interesting. I find that the critical value of the regularization needed in the loss function is tied to how the Hessian and the gradient norm square blows up at infinity. And this Villani condition forces you a certain value of the regularizer to get this blow up. And this maybe is improvable. I'm not claiming this number is optimal. It's likely the number can be lowered quite a bit by more fine analysis in future. That's completely an open question. Note that the gradient Lipschitz condition is required basically to convert from SDE to SGD. The SDE convergence does not need the gradient Lipschitzness. If you give up on the gradient Lipschitzness in a natural way to use soft plus activations, so smooth ReLU, you can use the theorem on smooth ReLU. You can use the setup on smooth ReLU, which is a soft plus, and SDE will still converge. The SDE convergence will still work out, but then you cannot convert from, we don't know how to convert from SDE to SGD for soft plus. But interestingly enough, soft plus, when you invoke this whole analysis above the critical threshold, it turns out the convergence is linear actually. It's a linear time convergence. You can get exponentially fast convergence in multi-gate scenarios once you're critical above a certain critical amount of regularization. Any questions so far? I have enough time. I can take questions here. Are there questions?
Can I very briefly ask a quick question? I missed what exactly was the regularization. Do you just add the norm of the weights to the training loss? So,
yes, there's a standard Frobenius norm regularization. You
okay.
can see lambda by 2 WF square.
Yeah. Thank you. Okay.
Thank you. Any further questions before I get into some comments about what this is saying? There's some things to understand here about the soft plus convergence I've shown. So now, one of the questions one can ask whenever you see a regularization is to say that, how do you know you have not regularized too much? So there's a question that often gets asked. One sanity check that our regularization is not too much is to do an ablation study. What I mean by an ablation study is that I will add extra noise into my training data, and I will run the algorithm at different amounts of noise in the training data, while keeping the regularization above my threshold. And what you see here is that the train error as well as the test error both show gradual degradation as I'm adding more noise. Which means that when I'm making the squared loss part of the loss function more and more bad, my performance is going bad, which is an evidence that my regularization did not overshadow the mean part of the loss function. I'm still able to get an ablation effect. This is one way of saying this, that your regularization is not too high. Now, let's think of it in a slightly different way in terms of what is known and not known in this field. So I like to show this diagram, where what you see is on the x-axis of the diagram, you see amount of regularization that you can use. And I have varied the amount of regularization in the x-axis from 10 to the power of -5 to 0.13, which is above the threshold of proof. So the red vertical line that you see here is the Villani threshold, or the critical threshold at which our proof kicks in. To the right of the red line, or for all regularization values to the right of the red line, our proof will work. And once you go left of the red line, no proof works. So the entire yellow region is where theoretically there is nothing is known. There's no theory that works in this zone. Finite data, finite width, arbitrary data, regularization is below this threshold. There's no proof in this zone. The first time any proof starts to work is once you are hitting this Villani threshold and our proof comes into play. And I've shown that, and what you see here is that at different widths I've tried it. Some are underparameterized, some are overparameterized with respect to the data. And I've shown that there is very small amount of damage to the test error that happens because we are not working at the lowest possible regularization you could work at. So there's a very small damage compared to what you're giving here. And this can be shown to happen. And this particular data is, you can see some sinusoidal function that we picked up to do this experiment. And one can show this experiment both in realizable data or non-realizable data. And the phenomena essentially remains the same. Then there is a very small amount of damage that happens to the test error because of working at the Villani threshold as compared to not working where you are. But of course, this puts into perspective that so much is theoretically not known. The whole yellow part is where there is no mathematics. There is no mathematical proof at this point of what happens in the yellow part of the graph. First time any maths is at all kicking in is to the right of the red line, which is where this proof is. I think it's an interesting way to see the theory space of what is known and not known. Okay, and let me try to go over some next steps that is possible. Notice that this proof is currently tied to the squared loss with the regularizer, but there is no fundamental reason I know of at this point why it should be tied to squared loss with the regularizer. It's very natural to ask whether this Villani function effect will kick in for other losses. And I think that's a very important research question going ahead. A very deep question here is to understand the Poincare constant of the Gibbs measure of neural nets. What is the Poincare constant? I don't know at this point. There are a lot of things that one can ask about it. How large is it? When is it small? When is it big? And so far, we did not have a very good reason to do research on the Poincare constant of neural nets, neural measures. But now we have, because now we know that the Poincare constant of the neurally induced Gibbs measure is precisely the time scale of SGD convergence. So if the Poincare constant goes up, your SGD will take longer to converge. If the Poincare constant is low, it will not take. So now we know in a very precise way that the runtime of SGD on neural networks scales with the Poincare constant of the Gibbs measure. What is the Gibbs measure? This is a very complicated question to figure out. And a lot needs to be understood here. Knowing Poincare constants of measures is a research field on its own. But now we know that we need to do that research for neural nets specifically. Third, last thing I want to talk about is, okay, this single net neural nets are they can only do so much. Now we are in the regime of double net training. So one of the very famous neural architectures that has come about in recent times is what is called a deep operator network, where you take two neural nets and you take an inner product of their outputs to get the final output, which is one is called a branch network and other is called a trunk network. And one can argue that one can prove, it has been proven that this product of two neural nets can approximate any map between any two Banach spaces. So maps between any two infinite dimensional Banach spaces can be approximated by a product of two neural networks. Once you have this universal operator approximation theorem, it as a corollary tells you that you can solve PDEs. So large families of PDEs can be thought of as solutions to large families of PDEs can be thought of as maps between Banach spaces. So what can approximate maps between Banach spaces can hence solve PDEs. It's a one-shot training for infinite number of PDEs in some sense. And that's exactly what is doable by deep operator networks. So in this paper, we had given the first width-independent Rademacher complexity bounds for deep operator networks. And so that shows that generalization error is controllable. There is some control of the generalization error which won't blow up with the size as badly as you think it might. So there is some control of the generalization error now, but no one has shown provable training for operator networks. As far as I know of, there is no result out there on provable operator network training. So a very interesting next step could be to ask whether the Villani function proof technique can open up this field. But now we have a whole new way of understanding SGD convergence, and maybe this is enough to get you operator network training. And hence you will be able to show that SGD can probably solve PDEs in this very particular sense. That's now a possibility. Okay. I'd like to end the talk with my affiliation. So Center for AI Fundamentals is where I work at.